I tried, basically what I did with the review is how the exam is going to be structured is like that. One question is going to contain a lot of the concepts that you learn. Like as you'll see in one of the review questions, like find the orthonormal basis to the orthogonal complement of the image of a matrix. So that literally has like 10 concepts in it that you need to know, like if in order to talk about. So I self-contained a bunch of things into one question. That way I can grade my sheet faster and also it'll all be very nice and neat for you guys just to do. Uh, okay, but before we do that, let's just go over linear transformations. So question, um, I guess, what is a linear transformation? Well, to put it in layman terms and just I guess in terms that I guess make sense. So basically, if you know for real numbers in college algebra, you guys studied functions. You have even functions, you have graphs of functions, you have basically everything there. For functions, you have a. They always describe it as a machine, right? The function eats a real number and spits out a real number via a rule. Like it can be x squared, right? Like it takes in the real number x and spits out x squared. Well, linear transformations are literally just the analog of functions, but in vector spaces. So linear transformations eat vectors and spits out vectors. That's basically what it is. It's a function for a vector space. So answer, it is like a function, but for vector spaces. Yep. Okay, well, since we have functions, since it's like a function, then we have the concept of domains and ranges or images, right? So literally, so if you have something like, here's my V, let's say this is the domain, and here's my W, and this would be the, I guess you would say codomain in this case. So you have a vector here in this vector space, and it's V, and so basically it gets mapped to this vector over here called W. So everything that, and then we call the linear transformation L, basically. So L maps V to W, okay? So everywhere that L maps to, or the range, this, like if it only maps to this part right here, this part is called the range, the little red stuff here, right? Like the function f of x equals x squared. The domain is all real numbers, and the range is all positive, 0 to infinity, right? It's not all real numbers again, it's just from 0 to infinity. Same thing. A linear transformation only maps a part of the vector space, or it can map to the entire thing. In that case, it'll be a surjection. But yeah, so we have this concept of domain, codomain, and range for linear transformations. Again, it eats a vector, spits out a vector. I guess maybe I should say, well, let's just keep it as a. No, it won't be it's just I just need to like get through this because, well, it's we need to get through chapter 6 and some of chapter 7. So example, define. Oh yeah, by the way, this is section 6.1, which is intro to linear transformations. Okay. So example 6.1.1. Define a linear transformation L from V, or actually rather, let's say the vector space R2 to R2 as L of, so it takes in a vector x1, x2 in R2, and it spits out the vector x1 minus x2, x1 plus 2x2. Okay, so this is the rule we assign. So let's just say find the image of, I guess, the vector v equals -1, 2. Okay. Well, how do I find what happens to I mean, what is this? So what happens to v under this transformation? So I mean, literally just do this. So L of -1, 2, and then this will give me, well, just plug it in. It'll be -1, be -3, and then it'll be 3. So the image of -1 to 2. So basically what happened is this. Here's R2, and here's R2 again. Yeah, we're reviewing. I'm just gonna do half this class, this stuff, and then the other half will start review. So what happened to this vector, -1 to 2, is that this went over here, -3, 3, under L. Okay, so that's what happened. L mapped -1, 2 to -3, 3. Okay, perfect. So now we have somewhat of a picture idea of what's happening. So now let's actually give a formal definition of what a linear transformation is. So remember, a linear transformation is a rule that you, like f, you can define f to be whatever, right? I mean, sine of x, whatever you can come up with. Same thing, L, you can define it to be however you want. The only thing that is required of a linear transformation is what I'm about to define. So let's see. So definition. So let, yes, V and W be vector spaces. Over a field F. The, I guess, function you can say, L from V to W is a linear transformation if it satisfies these two things. Well, actually, you can just say it satisfies this. If for any scalars alpha, beta in my field, L of alpha times, and V and W and V is equal to alpha L V plus beta L. Okay. So literally, it distributes, right? Like L distributes it. If the rule that you come up with does this, then it's called a linear transformation between two vector spaces. So remember, just FYI, since this will, what additions? Where is this addition happening, and where is this addition happening? Are those the same additions? I mean, there's only two answers, right? So I guess you can just guess yes or no. Yes, it's not, right? because this over here is addition. Yeah, I mean, yeah, you're like hitting on it. Basically, this is addition in the vector space V, and this is addition in W, right? So these two additions are different. Remember, every vector space comes equipped with an addition, right? See, these the V and W are two different vector spaces. So that addition is in V, that addition is in W. So remember, just I guess keep this in mind because it is an important distinction to make. Okay. Okay, so we still have enough. So let's state a theorem. 6.1.1. So let L from V to W be a linear transformation and I guess you can say V and W be in V, okay? Then the following holds. So L, the linear L applied to the zero vector is always just a zero vector. L of the negative of V is just going to equal to negative L of V. L of U minus V is equal to L of U minus L of V. And I guess if V is a linear combination of, say, vectors in like this, then T of V, or sorry, not T of V, I keep using T. L of V is going to equal to C1 L of U1 C1. So these are just nice properties to have. We're going to actually use the fourth one soon for something very special. Okay, so now before we get to some examples, I'm going to I'm gonna now tell you this. You guys actually already know one type of linear transformation. Does anybody want to guess what that is? I mean, there's only like so many things we talk about in this class. What is like the only thing we've really talked about other than vector spaces? Matrices, right? A matrix is a linear transformation. I mean, don't you? I mean, take a matrix, apply a vector on it. What does it spit out? A vector, right? Like AX, if you take the matrix A, multiply it by the vector X, it gives me the vector B, right? So why can't A be a matrix be a linear transformation? Well, it's not that it can, it is, right? So we already know a type of linear transformation. Namely, matrices. Do matrices satisfy this rule right here? Of course, right? So observe that if you have a matrix A and you multiply it by some vector that's written as alpha times x plus beta times y. Well, matrices distribute, right? So it's just going to be a alpha x plus beta a beta y, and this is just going to be alpha ax plus beta ay, right? I mean, it satisfies the condition that we have for a linear transformation, and this gives you another vector, right? A multiplication by matrices gives you another vector. So matrices are linear transformations. Now I want to I guess make that formal. Before I give this warning out. So I guess theorem 6.1.2. Let A be, let's say, an n by m matrix with real entries. Then L from, say, okay, so let's see, sorry, so so takes in a vector from n. So now the function L defined as L of V is equal to A times V is a linear transformation. And the proof is literally just this. I mean, that's how you prove the theorem. So an n by n matrix takes a vector from Rn and spits out a vector in Rn. Okay. Let's see. Here's the warning now. Not every linear transformation is a matrix. Okay? So, just because I tell you something's a linear transformation doesn't mean it's a matrix. Okay? There are linear transformations that are not matrices. However, all matrices are in fact linear transformations. So all matrices are indeed linear transformations. Perfect. Anything that I want to add? Yes, I do want to add some stuff. Yes. So let's actually illustrate what I talked about in this warning with actually looking at a linear transformation that isn't a matrix. I mean, later we'll see that for any finite dimensional vector space, you can actually represent this linear transformation as a matrix. But for right now, let's just like have this warning and then look at some that aren't. So examples. Example, let's say 6.1. How many do I have here? Show that a linear transformation goes from the set of n by n matrices with real values, the vector space of this, to the set of n by n real values defined as L of, let's say, it takes in a matrix A, and I define it as taking the transpose of it, okay, is a linear transformation. So clearly this rule isn't a matrix rule, right? I mean, the rule is just take the transpose, but this is indeed a linear transformation. So how do we show it? Well, let x, y be in n by, I guess maybe I should say something a little bit better, like let A and B be in an n by n matrix with real values, and alpha and beta be just real numbers. Then, okay, L of alpha times A plus beta times B is going to equal, well, what is this going to equal? So by the rule, what is this equal? Huh? Yeah, the transpose, all that stuff, right? So it's just going to equal the transpose of all this stuff, right? And if you remember, we had like a theorem for matrices when we were talking about matrices in chapter 2. What is this going to equal? What's the transpose of the addition of two matrices? Just the transpose of each one added together, right? So it's going to be alpha times A transpose plus beta B transpose, right? And then constants can just come out of that. So let me put this over here, actually. So this is just going to be alpha times A transpose plus beta times B transpose, right? But that's just going to be alpha times L of A plus beta times LB. So this is indeed a linear transformation. All right. Let's look at two more examples, and that pretty much just finishes the introduction towards linear transformations. Example 6.1.2 or 3, sorry. Let C1 from A to B be the vector space of all linear, of all continuous, all functions whose derivative is continuous. Okay, so like sine, right? Sine, taking a derivative as cosine, that's also continuous. Show that so we're going to say differential operator d of x, which is defined on f to be just the derivative with respect to x of f, is a linear transformation d from, or dx from C1 from A to B to C A to B. Okay. So you see, this is a linear transfer. Well, we're about to see that, but okay. So solution. All I'm going to do is let f and g be in C1 from A to B, and alpha and beta be in real numbers, right? So all I have to show is that this is linear, right? It should show it's a linear transformation. So dx of alpha f plus beta g. Well, what is, again, what by definition, what does this do again? This operator thing? What did I define it to be? I mean, it's right here, right? This is what I defined it to be. So what does it do? Yeah, exactly. So it just takes the derivative of that, right? So it takes the derivative of alpha f plus beta g. What can I do with derivatives over sums? I can just distribute, right? I can take the derivative of each individual one instead. Derivative of alpha f plus the derivative beta g. Okay. What can I do with the scalars? Can I pull them out? Right? I mean, taking a derivative of something with a constant in front, I can just ignore the constant, just take the derivative of what's left. So this is just going to be alpha d dx of f plus beta. Sorry, hold on. D dx of g. Let me make this a bit smaller. But this is equal to just alpha dx of f plus beta dx of g, right? So this is indeed linear. And it's a linear transformation between the vector space CAB to CAB, right? I mean, so clearly this isn't a matrix, right? This is just a linear transformation that is not a matrix. So let's look at one more, and then we'll start doing the review. Six point 1.4. So define a linear transformation from, say, P2. No, sorry, Pn. Or not even. Let's just say P. To R. So P means a set of polynomials, and it can be infinite. It can be infinitely many. As this. So L of a polynomial P, define it as the integral from A to B of P of X dx. Okay. Show that L is a linear transformation. Literally just do let P and Q be a polynomial, and alpha and beta be real numbers, right? Then L of alpha times P plus beta times Q is going to equal the integral from A to B, right? This is how we defined it, of alpha P of X plus beta Q of X dx. So what can I do with the integral on here? can I distribute the interval? Yeah, right. So I can just distribute and take out the constant like this. And this is just going to be alpha L of P plus beta L of Q. And so it's linear. Okay. So that's basically introducing what linear transformations are. I just wanted to hit the big picture stuff. Here's the big picture stuff. Linear transformations are functions between vector spaces instead of real numbers. Linear transformations, matrices are linear transformations, but not every single linear transformation is a matrix, as illustrated by these two examples, or even three examples, right? All three of those examples were linear transformations that were not matrices. And okay, that's pretty much what I want to say about that. Next time you go, so now you might be asking like, why, who cares, right? That's usually what I always say is like, who cares? Well, you care a lot because they play a very important role in many, like I mean, I've been saying it with a lot of things, but it's true. You have these things that are like applied almost everywhere, like rotation matrices especially. Next time we'll basically just see that for finite dimensional vector spaces, every linear transformation, well, the set of linear transformation is isomorphic to matrices. So you can actually just consider the linear transformation as a matrix for finite dimensional vector spaces. But yeah. Okay. So okay, so let's move on to the review. Let's erase this. Sorry, I was just helping someone with something. Okay. So, like I said, the midterm is going to cover everything in those past two chapters. And in those past two chapters,
hello there.
We covered a lot. So, first of all, question number 1. Right. So, prove that the vector space like I said that for the vector space V is equal to the set of all functions from some interval to R, such that the first derivative and the second derivative exists. The subset S equals Y and V such that it satisfies this. Is a subspace. Okay. So if you guys are proving something to subspace, what do you have to check? The what? Sorry, what was that? Yeah, closure. Yes. Yes, yeah, closure for addition and multiplication, right? And there's one more thing. Yeah, like zero vector, right? We need to know if the zero vector is in here. Okay. By the way, this is C2 from on I. This we can also consider. But I mean, so what is it? So with the standard addition and scalar multiplication for functions, what was always a zero vector considered in that case? For functions, right? For functions. What do we consider to be the zero vector for continuous functions? Yeah, exactly. The function f of x equals 0, right? I mean, that's a function, right? The function f of x equals 0, it would be considered a zero vector and for this guy. So, okay, so by the way, so what I mean by this like little dash, I'm pretty sure you guys you already know, but it just means the first derivative and the second derivative, right? So, first question, is f of x equals 0 in S? So is S is the set of all functions y and v such that it satisfies this equation. The second derivative minus the 4 times the first derivative plus 3 times the function itself equals 0. So does f of x equals 0 satisfy that equation? By the way, it's a differential equation, but it does, right? Because, so I guess let's use the notation there. Let y of x equals 0. Yes. Why? Because y of x equals 0, y prime of x is equal to 0, and then y prime prime of x is equal to 0, right? Plugging in into y prime prime minus 4y prime plus 3y equals 0, you get, well, 0 minus 4 times 0 minus 3 times 0, which equals 0, which if you just do this, it's going to say 0 equals 0. And that's so that means it's satisfied, right? Yeah, I can zoom out. Zero space vector. So, no, it just means zeros. Yeah, it just means, so that means right here that f y of x equals 0 is definitely in S. That just means zeros in there. Yeah, exactly. If there was a plus 5 at the end, then then 0 wouldn't be in there, so that would no longer be a subspace, right? So it's necessary that this doesn't have just some constant like floating on at the end of it. Yes, but yeah, 0 is in here. So the 0 vector is in this set. All right, what's the second thing? Well, some of you already mentioned it, but we need to show it's closed under addition, right? So how would you show that? So first step is always good to take y of x 0 because we picked it to be so again I guess maybe we should go back to this set right here, right? It's the set of all functions on the interval from I to R such that the first and second derivative exists, right? What do things in there look like? Well, polynomials like x squared plus 1, sine, cosine, e to the x, ln of x. Are numbers in there as well, like the number 2, 3, and 4? Yeah, they're just constants, right? Constants are functions. So 0 is definitely in V, right? So what we were trying to do is then show that the 0 vector, which in this case for this vector space is the function y of x equals 0, is inside S. That's why we picked y of x equals 0. We had to show that that thing was an S. Okay, okay, let's move on to the second part. Ignore this. The second thing we need to do is show that if F and G are in S, then F plus G is also in S. We need to show this. We need to show, right? Okay. So how will we even do this? Let's say y. Let's just say y1 and y2, just to keep the notation consistent. So, okay. So what do you guys think we'll do? Well, what does it mean to be a member of S? Like, can any function just be in S? Like, can cosine be in there? Well, no, right? I mean, if you try to solve this differential equation, you'll see exactly which ones are in there, but that's not the question, right? What does it mean to be a member of this set S? If you wanted to like be here, what do you need to satisfy? Well, you need to satisfy the equation, right? The differential equation. Yeah, exactly. So we need to show that y1 plus y2 satisfies it, right? So we need to show that y1 plus y2 satisfies, what was it? Y prime prime minus 4y prime plus 3y equals 0, right? We need to show that that satisfies it. Okay, well, just plug it in. So we're going to get y1 plus y2 prime prime minus 4 y1 plus y2 prime plus 3 y1 plus y2 equals 0. Okay. So what do I do now? Well, can I take the derivative of each one individually? Yes. Yeah, exactly. So this would just be y1 prime prime plus y2 prime prime minus 4 y1 prime plus y2 prime plus 3 y1 plus y2 is equal to 0, right? All right. So now what I'm going to do is I'm going to rearrange things, okay? So I'm going to rearrange it like this. y1 prime prime minus 4 y1 prime plus 3 y1, and then I'm going to get plus y2 prime prime minus 4 y1 prime, y2 prime plus 3 y2 is equal to 0. Now, what do I know about those terms? They equal 0. Why do they? Right. Well, just when the original equation is that, that's the expression, right? But why does in particular y1 being plugged into there give me 0 and y2? Yeah, because they're both in something. So since y1 and y2 are in S, they have to satisfy that equation, right? Meaning they both have to be equal to 0. So yeah. So they said a subspace condition. Yeah. So these have to be 0 necessarily because y1 is an S and y2 is an S. So that means that you get 0 equals 0. So they y1 plus y2 is indeed an S, right? Okay, so it's closed under, oh my goodness. So the third thing is what? Scalar multiplication, right? So let y be in S and lambda be in R, I guess. Then what? We need to show that lambda. Then we need to show that lambda y is also an S, right? Well, again, how do I show it's lambda y is an S? In this case, what would you have to do? Well, just plug in lambda y into the equation, right? Just plug in. I guess I should say y1 just to distinguish it. So lambda y1 times y prime prime plus or minus 4 lambda y1 prime plus 3 lambda y prime lambda 1 equals 0. Okay, this is just going to be lambda y1 prime prime minus 4 lambda y1 prime plus 3 lambda y1 is equal to 0. So what can I do after this? Can I conclude it's 0 yet? What can I do? Yeah, factor out the lambda. Y1 prime prime minus 4y1 prime plus 3y1 is equal to 0. And what do I know about this? It's 0, yeah. Because y1 is an S. So that means that you get 0 is equal to 0. So that means that lambda y1 is an S for sure. So this thing is a subspace. Perfect. Any questions on this one? So remember, that's all, no matter how complicated the subspace is, you always check those three things. Right? You always check those three things. You never check any more. Okay, next one. So the next one says that you have this matrix A. Sorry. So it says that we have this matrix, right? It says find a orthonormal basis for the image of A. So number 2. So we won't be able to like finish it up, but so it says find a orthonormal basis for A is equal to 5, 2, 3, 4, 3, 0, 2, 3, 0. So this you have to know a lot of things, right? How do you find the image? What is the image? Yeah, you can do RREF. Okay, so what do you do after you RREF? So, by the way, so let me ask. Uh, not, not the vector form. What is the image defined as, or the column space of a matrix defined as? What is it? Like just forget about the REF thing for a second. Like, what do we call the column space? No, you don't have to show the REF. You can put it in the count. Okay, basis. Someone said basis. Basis of what? I mean, okay, so you take the basis of the row space, and what does that give me? Yeah, take the span. There we go. By definition, the span of the columns A is the column space. Now, how can you get the column space? Well, you just take the span. However, yeah, and then you have to use the Grant-Schmidt, right? That's a good point. But anyway, so we ran out of time, but think about it, right? Because again, this is you're using a bunch of stuff here that you need to know. Yeah, we'll finish it this Wednesday, and then I might include one more review session, but I'll try to finish it Wednesday. If I don't finish it, I'll finish it sometime later that afternoon on Wednesday, or on Thursday morning, something like that. Okay. Yeah, it's open all day Friday. Yeah, it's same format. It'll look like the review, except I'll change some things. So one of the questions on the review, I'm gonna completely take out and replace it with another one, but it'll still be the same concept kind of thing. Okay. Yeah, open notes all day until midnight. Yeah, we can do later with primer practice. Yes. Alrighty. I'll see you guys Wednesday. Which? Oh, I can't tell you that. I can't tell you which one. Just know how to do all of them, and then you will have no problem. Of course, yes.